Now I can record. Okay. Okay. So we can do all these calculations over here, and then we can gradually reduce it. So now we started from here. So we took the three paths. In this case, in this critical path method, we took three paths: ACF, BDF, and BEF. And then for each of these paths, the duration along the activities along these paths was 11, 8, and 9 days. Okay. So from 11, 8, and 9 days, so we have the longest path is the 11 days. And then from 11 days, if you want to reduce it to 10 days, so we have to choose one of those activity for which we can reduce the duration by one time unit. So in this case, we chose activity C because activity C was the cheapest over here. So therefore, reduce this activity by C by 1 day. Similarly, by each time we will inspect these three paths, and then we will choose some of the activities. So in the second crashing, we choose the activity C. In the third crashing, we choose two activities A and B. And in the fourth crashing, we choose two activities A and E. But by doing this, we have actually fully crashed this activity, fully crashed this path as ACF and BEF. So once we have fully crashed any of the path in the network, then you cannot further reduce the duration of the project. That's why we can see that we did not crash activity D at all, because activity D was not needed at all, because it may have some kind of slack available or like that. So the reducing the activity D will not reduce the duration of the project in this case. So in the end, we got the 7, 7, and 7 days of the project duration. Okay.
Okay, it's okay, Professor. I got it. I got the point. I just missed the first part. Yeah, no, it's clear.
Yeah, I was continuing from the previous last week where we finished it.
Yeah, thank you.
Okay.
Thank you.
Okay, so yeah, so this was one of the example for this time cost optimization, and then I did something, and then I did it on the Excel as well. Okay, so maybe I put it now in the recording, because earlier I did not put it in the recording, but now this chart is also in the recording, so maybe then you can get an idea how I created this chart. So okay, so that was the time cost optimization. Okay, next I think which I want, because we are talking about the topic of the risk, and the risk topic we can consider in many ways. In this case, for example, we took the before we also took the example of risk with simulation as well. Now we can also consider the example of the risk by the method which is called as the PERT. Okay. Okay. Just forget about this. This is for some other course, but anyway, we can still use this these slides. So program evaluation and review techniques. Okay. Program evaluation and review technique. Okay. PERT. So this PERT method, we are now discussing it for understanding the how we can also take care of the concept of risk in the duration of the activities. That, for example, in those situations when we are uncertain about the duration of the uh, activities, so we will have three types of time estimates for the activities. So we use a kind of we use a technique which is called as the program evaluation and review technique, PERT, for this purpose. Okay, so let me explain this technique. Okay, PERT. So PERT is the let me make it like this. So program evaluation and review technique, it is an event-oriented network analysis technique used to estimate project duration when there is a high degree of uncertainty with individual activity durations. So PERT applies the critical path method to a weighted average duration estimate. So PERT is considered a probabilistic or stochastic method. Okay. I think these concepts will be clear when we are going to look at something more about this. So in this case, in PERT, for each activity, there are three durations. Those three durations for each activity must be calculated. One of that duration we call as TO, which is called as the optimistic duration. The other duration is called as the TM, which is the most likely duration. And the third duration is called as the TP, which is the pessimistic duration. So from these three durations, the expected time for the completion of the activity is calculated by this formula. TE is equal to T naught, TO plus 4 TM plus TP over 6. Okay, so optimistic duration is the minimum possible time for which you can complete the activity. Okay, you without considering any crash cost or these kind of things, you say that, okay, if everything goes well, then how early this activity week I can finish. So that will be the optimistic duration. Most likely duration will be that duration in, say, we will say that, okay, if I perform this activity, say like 10 times, maybe like 9 times, uh, I may be able to complete this duration, this activity in that amount of time. So that will be the most likely time. And in the pessimistic duration, I will consider that, well, the things are not going well with the project. And it may happen that as something will not go well, then the activity will be delayed, and then the activity will be finished in a much longer time frame. So it will be the pessimistic duration. So the expected time is then calculated by this formula for this activity. In this case, the most likely duration is given a high weightage than the optimistic and the pessimistic duration. Okay, so expected time for the activities is calculated. After that, we need to also calculate the standard deviation for each activity. So the standard deviation for each activity in this case will be simply the pessimistic duration minus the optimistic duration divided by 6. Okay, pessimistic duration minus optimistic duration divided by 6. And we can use these parameters for further calculations. So from the standard deviation, we can take the square of that, and then this will give us the variance for the activity. So we will perform these calculations for each of the activities on the critical path. So for each path in the network, we will calculate the expected time for the path, which will be the sum of all the expected durations. So for example, if there are A, B, C, D, 4 activities, for activity A, we will calculate the expected time. For activity B, we will calculate the expected time. Similarly, for activity C and D, we will do these calculations. And then we will add up all these expected times. So this will be the expected time for the path. And similarly, we will sum up all the variances and the sum of, and then from the total variance, we will take the square root, then we will calculate the standard deviation of the path. So in this way, we will go with the process. So after that, after doing this, then we will calculate with this information just calculated for the examined path. We can calculate the probability that an event will occur on or by the certain date, TS, by using the normal distribution formula. So the normal distribution, for this normal distribution formula, we will calculate the value of Z, the value of Z. So value of Z will be simply the ratio of this times with the standard deviation of the paths. So that means the more the value of the Z, the more more away will be from the expected duration. Okay, so we will calculate this z function, which represents the number of standard deviation, uh, which represents our position. This z represents our position from the by the number of standard deviation away from the mean value, which is taken as TE. Okay, so this is some brief theory about the uh, PERT. And this PERT uses these tables. These tables are the cumulative probability distribution tables. Okay, we can even use Microsoft Excel as well to directly calculate these values, but uh, we can also use the table. So there are two ways. So one, we can use it from the Microsoft Excel to calculate these values, and the other is the table. So in this example, we will use these tables. So these are the cumulative probability for the standard normal distribution. So for different value for the different values of z, we can calculate the probability for the occurrence. Okay, so for example, for a value of z is equal to 0, the probability of occurrence will be 0.5, that is 50%. For a value of z equal to 1.5, the probability of occurrence will be 93.32%. So we can use these tables. Okay, so I will take the one example to illustrate all these points. Okay, so as an example, let's see that we have a CPM network, critical path method network. And in that critical path network, there is a critical path which includes 5 activities, A, B, C, D, E, okay, 5 activities. And their durations are tabulated as below. So for example, for activity A, there is an optimistic time, most likely time, and the pessimistic time. So for each of these activities, optimistic, most likely, and pessimistic times have been calculated. So okay, given this data, and using the PERT technique, can we calculate different probabilities for this project? So for example, in this case, 9 different probabilities have been asked to calculate. And what are those 9 probabilities? So just see, for example, what is the probability that the project will finish by the end of day 32? Okay, if you look at this data, remember that this is the data for the critical path. Okay, so A, B, C, D, E. A, B, C, D, E is the critical path. So we are just taking out of a critical path network, because in the critical path CPM network, there may be several paths. Okay, but for simplicity, or for just for the illustration of this method, we are only considering one path, A, B, C, D, E. Okay, there may be some more paths as well, but we are only considering this critical path, because critical path is the one which controls the duration of the project. Okay, so if we take this critical path A, B, C, D, E, and if we take the most likely duration, then what we can see over here is that what is the sum of the duration on the critical paths for the most likely situation? So 12, 6, 12 plus 6, 18 plus 2 is 20, and 20 plus 10 is
30.
13. Okay, 20 plus 10 is 13. 30, yeah, 30, 30. Okay, so that means if we just take a case in which we don't have any risk involved, we don't involve any risk, we can say that the project will finish in 30 days. Okay, so that will be our simple answer. However, it is not the case. The case is that the duration of the activities are not certain. Although the activity A can most likely finish in 4 days, but there is a chance that the activity may finish much earlier, or there is also a chance that the activity may finish much later. So similarly for other activities as well. So since there is a chance that activity can finish early or later like that, so this the situation becomes quite complicated. Okay. So for one of the approach which we did in the last week was that we used the Monte Carlo simulation for that purpose as well. So that is also one of the thing which we can do. But in this case, we are using another method which is called as the PERT. Okay. So in this PERT approach, we can also deal with this type of situation. So what is this case? So in this case, so for example, although we can say that the normal duration for this project will be 30 days, but the project can finish in other than 30 days as well, maybe less than 30 days or maybe more than 30 days. So for example, if the project finishes in 32 days, so what will be the probability? That means 50% probability, 70% probability, 30% probability, whatever that probability. So this PERT method will tell us that probability. Okay. So this PERT method will tell us that probability. Similarly, what will be the probability that the project will finish by the end of day 34? And what will be the probability that the project will finish before day 30? And like that, different questions have been asked. Okay, so just look at these first two questions and now think about it and tell that in which case the probability will be more. Whether the probability will be more to finish the project in day 34 or the probability will be more in to finish in day 32.
The probability will be more in 34.
Yeah, so it will be more probable. It will be more probable that the project will finish in day 34. Okay, so by just our qualitative assessment, we can answer that. But what will be those probabilities? So that we will see it. So for this, we will be adopting this methodology. Okay, we will calculate the expected time for each activity. We will calculate the standard deviation for each activity. We will calculate the variance for each activity. And for each path, we will calculate the expected time for the variance and the standard deviation. And then we will calculate these Z values, and then we will look at these tables. Okay, so this type of process we will have to do this. So here, these things have been performed over here. Okay, so we took the same data as before, like this. This is the same data. So this first three columns are the same data. Now we calculated the expected duration. So from 2, 4, and 7, the expected duration is 4.167. Do you agree on this? Yeah, so 4.167 is equal to 2 plus 4 times 4 plus 7, and then divided by 6.
Yeah, 25 divided by 6 is 4 point.
Yes, and then for B, just you can just in your head you can verify it. Okay. Correct?
Why we divide by 6?
Yes,
Yeah.
correct.
We will divide by 6. We will apply this formula.
Okay.
Expected time, this is the formula for the expected time. Okay, so we will divide, we will take the optimistic time, we will take the pessimistic time, we will add them together. We will take the most likely time, we will multiply it by 4 and then add them with the other and then add everything with the divide everything with the 6. So we will get these values over here. Okay. Now for the standard deviation, so what we will do is we will take 7 minus 2 divided by 6. 7 minus 2 is 5. 5 divided by 6, it will standard deviation. 14 minus 5 is 9. 9 divided by 6 is 1.5. So in this case, we can get the standard deviation. Square of the standard deviation will be the variance of the activity. So we'll just take the square of this. 0.833 square of this is this. 1.5 square of 1.5 is 2.25. 0.667 square of that will be 0.444. Okay, so once we calculate everything, calculate this, we will add up all the durations, expected duration over here. So 4.167, 8.56, 2, and 11.33, it will be 32. So yeah, incidentally, it is a round figure as 32 over here without any decimal places. So if you will add all this together, it will be 32. And if you will add all these variances together, it will be 8.833. So now this TE, remember that this T small e and T capital E, there are two different terms. T small e is for the expected duration for the activity, whereas T capital E is the expected duration for the project. Okay, so expected duration for the project in this case is 32 days. 32 days, and the variance for this project is 8.833 days. So we need this variance later on. We will take the square root of that. That will be the standard deviation for the project duration. Okay, so all the calculations in this table are clear. Then next is that to answer the first question, what we do is now we took TE is equal to 32 days, which will be from the previous case. VE was 8.833 days, and we take the square root of that. That will be the standard deviation of the project. Okay, standard deviation of the project. So now we can answer these 9 questions one by one. So what were those 9 questions? So for example, the first question was the probability that the project will finish by the end of day 32. So using these values, so for especially these 32 days and this standard deviation, we will calculate the Z function. So what is that Z function? Z is equal to the TS minus TE over sigma E. So TE we calculated, sigma E we will calculate it, and TS is the given time. The given time in the question. Okay, TS is the given time in this question. So the given time in this question is 32 days. So probability that the project will finish by the end of 32. So it is TS. TS is 32, and TE is incidentally also 32. So 32 minus 32 and then divided by 2.972. Of course, that will be 0. And that will be 0. So for this value of 0, that means it is exactly lying in the center of the normal distribution curve, because this Z is the difference. Z shows the difference from the center, difference from the mean, and the normal for the normal distribution curve. For example, if I can draw it. So the normal distribution curve, oh, what is this? Yeah, for the yeah, so this is kind of like normal distribution curve. Okay, so and here we have like this. Okay, so when we talk about the z is equal to 0, so we are on at this minimum at this vertical line. Okay, that is, and then when there is a value of z is equal to plus or minus, then we are towards the left, towards the right and left of this curve. Okay, so in this case, we can we can see that there is now 50% chance. Well, there is a 50% chance for this project that this project will end at the end of day 32. So this we can also see it very easily in this table as well. From the table of z values. So we can read this z value, z is equal to 0.00. So the probability is given as 50%. Okay. So in this case, we can say that it's the probability for finishing the project by the end of day 32 means that the project will finish by the end of day 32 or earlier. TS is less than or equal to 32, it is 50%. Okay, so what was the next question?
34.
Yeah, so this we can represent, yeah, for this 50%, we can represent it like this, okay? So this is the distribution of the project duration. And you can see that we are exactly in the middle. So when we are exactly in the middle, then that means the probability is 50%. So this shows the 50% probability. So that means from 0 to 50, okay? This shows the 50% probability. So remember that we in this the PERT, as you can see from this chart, is also that the PERT assumes, the PERT method assumes normal distribution of the project duration. You can see that the PERT is assuming this normal distribution of the project duration. Okay. So the average value was 32. So the duration of the project is normally distributed along this case. So that makes it easier for us to estimate the duration of the project. Okay, so the second case was the probability that the project will finish by the end of day 34. So we can see that in this case, Z will be 34 minus 32 because now TS is 34 and TE and sigma E were, we have already calculated. So we will reuse these values for in each case. Okay, just recall that we calculated these values, sigma E and TE. Okay, TE we calculated from here and sigma E we calculated from the variance. Okay, so we will reuse these values of 32 and 2.972. Okay, so now we can see that TS is 34. So now 34 minus 32 divided by 2.97972. If you will calculate it, it will be 0.67. 0.67. So now we will have to read this 0.67 in the table. Okay. So we can see that where is this in this table? 0.6 is here. Z is equal to 0.6 is here. And where is 7? 7 is here. Okay. So here we have this 0.67. So the value is 0.7486. So 0.7486 means 74.86%. So here in this case, our answer is the probability for the project to finish by the end of day 34 is 74.86 or 74.9%. So which is according to our intuition that there will be a higher probability for the project to finish later than to finish earlier. Okay, because remember that I just asked a conceptual question before that. What is the probability that the project will finish on day 32, and what is the probability that the product will finish on day 34? And one of you have answered that there is a more probability that the product will finish on day 34. So we got the same answer. 32, the probability was 50%. For day 34, the probability was more, 74.9%. Okay, so these were the two questions which we have answered. So then, of course, there are some more questions as well. The probability that the project will finish before day 32. Okay, here, remember that you should be mindful of the wording of the question, okay? Finish before day 32 does not mean that finish by the end of day 30, okay? Before day 30 means finish by the end of day 29. Before, it is before date, because before day 30 means day 30 has not been, will not be included. Okay, so finish by the end of day or finish before day, these two statements are different. Okay, before date means that this 30th day will not be included. So it means that it will be the project will finish by the end of day 29. Okay, so this is how it has been done over here. So the project probability that the project will finish before day 30, this probability is the same as the probability of finishing by the end of day 29. Okay, before day 30 means day 30 is not included. So it means that by the end of day 29, before 30 is the 29th day. So 29 minus 32. Okay, so 29 minus 32. So now it is minus 1.01. Okay, minus 1.01. Okay, so here now we have the value of z is equal to minus 1.01. So in this case, so we will look at again the table. But in the table, I think which I have provided you in this slide, and I will share these slides with you later on, there are no negative values. So what will you do in this case? So there is a solution for that. Okay, so now I'm going to tell you the solution. So what was the negative value which I have found? The value of which I have found is minus 1.01. Okay, so for the temporarily, we will just ignore this minus sign. You will read the value for 1.01. Okay, in the table. Okay, remember that you will read just temporarily, you will forget about this minus sign and you will read the value of 1.01 in the table. So 1 is here and 0.1 is here. So 1.01 is 0.8438. Okay, so you will take this value 0.8438 and what you will do is you will subtract it out from 1. Okay, that means 0.8438 you will subtract it out from 1 in this case, because to take care of this negative value, you will take this you will read this the value of z from this positive part, and then you will subtract it out from 1, and that will give you the answer. So in this case, the answer is 15.6%. 15.6%. So which means that there is only 15.6% of chance for this project to finish before day 30 or by the end of day 29. So this is represented by this figure. So by the end of day 39, so you can see that very small area is shaded over here. Okay, a very small area. So this area just represents about 15%. Okay, yeah, 15.6%. Whereas in the previous case, by the end of day 34, a very large area was shaded. Okay, so that area represents about 74.9% of the total area under this curve. So does it make sense, these calculations? Do these calculations, okay, do you understand?
Yes, Professor, yes.
Okay, yeah, so, okay, so now that was the, now we have answered the third question. Okay, the fourth question is the probability that the project will finish on the 32nd day. Okay, so now again, I think we are playing with you by the words, okay? Okay, so this is the third variation of the words, okay? Here you can see that finish by the end of day 32, okay? Finish before day 32 and finish on the 32nd day, okay? So this is again different from the previous two cases, okay? This says that finish on 32nd day. So which means that neither before nor after, okay? Only on 32nd day. You got my point?
Yes.
Yeah. So it will mean that, okay, it will mean that which has been done over here. So the probability that the project will finish on 32nd day will mean that this will be the probability for completing the project on or before 32nd day and minus the probability for finishing the project on or before the 31st day. Okay. So this is actually, this is the probability for just that one day only, not any days before. So therefore, only the area in the 32 and the 31 day, that will be the answer in this case. Okay, so for 32 days, we have already calculated the probability before in part 1, that is 50%. And in a similar manner, we can calculate it for 31 days. So for 31, it will be 31 minus 32. That will be a minus 0.34. But since now we have the answer is as minus, we will just ignore this minus sign for it temporarily and just read the value of 0.34. 0.34. So read the value of 0.34 and then subtract it out from 1. So 0.34, the value is here, 0.6331. Okay, 0.6331. And then we will subtract it out from 1, that is 36.7%. So our final answer is the difference between 50% and 36.7%. So it will be 13.3%. So which means that the probability for finishing this project on 32nd day is 13.33%. And this probability we can represent by this shaded area. Okay, so this shaded area is the area of the is the area for the 31 and the 32nd day. So 32nd day is here. Okay, so the probability is this 36.67 days. Okay, so this was the question, and now the next question is the probability the project will finish no later than 35th day. Okay, no later than 35th day means no later than 35th day means 35th day means is the that 35th, no later than 35th day means before 35th day. That means it is this probability is the same as the probability that the project will finish by the end of day 34. So no later than 35th day, by the end of day 35. So this is the this is another way of saying the same thing. Okay, no later than 35th day means 35th day or earlier. Okay, 35th day or earlier. So here we can easily calculate it. So 35 minus 32 is 1.01. So it is, if you will see this value in the table, it will be 84.4%. And then you can say it like this. Next is this question number 6. So the probability that the project will finish at least 2 days early. So what does it mean by at least 2 days early? At least 2 days early means and this is the probability, the same as the probability of finishing the project on the 30th day or earlier, or the same as the probability that the project will finish by the end of day 30. Because 2 days early means the normal, the expected duration of the project is 32 days at 50% probability, but 2 days early means in 30th days. So for the 30th day, so you can now very easily calculate this probability, because only the things are that the calculations are repeating. So this probability will be 25.1%. And question number 7 is, and the probability that the project will finish at least 2 days late. So this probability is the same as the probability of finishing by the 34th day or later, or the same as the probability that the project will finish after day 33. Okay, so the probability that it will finish after day 33 will be represented by this. So that means the probability of finishing 2 days late is 36.7%. So in a similar manner, you will think about it, and then you will agree that the answer will be like that. So if you can see that graphically, it verifies our concept that 2 days later. Note that if the instruction has said that the probability of the project will finish more than rather than at least 2 days late, it would have mean that TS is greater than 34. Okay, so we have to be mindful of the wording of the question. And the 8th question is the probability that the project will finish on the 32nd day and plus minus 1 day. So this means that the finishing on the 31, 32, or 33 days. And then this, in this case, we will be adding the probabilities for these 3 days together, and then by simple manipulation of the probabilities, then we can come with that the answer is 38.2%. And yeah, I will quickly go to the last one, the completion date with at least 90% confidence level. So in this, for the 90% confidence level, you will pick a probability value which is close to or equal to 0.9, and then you will read the corresponding Z value. So in this case, we will find the Z value, and then we will, from the manipulation, we can calculate the TS value. So we will find the Z value from the table, and that it will give us like 36%, 36 days. So we are confident we will be, for 36 days, we will be 90% confident that the project will finish in 36 days. Okay, so that is the confidence level. Okay, so I think I have explained the main points in this topic, and then there is of course some other examples in this topic as well. I will be sharing with you this slide later on, and then you can read this slide, and then they can get a better idea of the program evaluation of this and review technique. So this program evaluation and review technique basically is used for research and development kind of projects. And here, there we want to know, in those situations, we are not very much sure about the duration of the activities. There is a lot of uncertainty involved. So we may want to get an idea of the probabilities for completing the project on some specific time frame. Okay, so that's all for today. So we will